This is our third part in the quarterly update for late 2022 of the MetBull update. So now we are in September. Sue, please give us the update.
Yes, this has been a whirlwind of a week. We did part 1 last Wednesday, part 2 on Saturday, and now we're here at part 3. So we are discussing the meteorite classifications that were approved and published in September of 2022. But before we jump into the MetBull update, wanted to ask you guys a question. Where do you guys think the best place to hunt for meteorites is? Don't all go at once.
The desert.
Arid deserts.
Antarctica.
Yeah,
That we can hunt, or that anyone can hunt?
Anywhere where they're easy to find.
I mean,
Well-
If I had to pick one place, it'd be the Atacama.
Hot and cold deserts where there's some sort of a concentration mechanism is my answer.
Yes, I heard a lot of good feedback. Okay, so yeah, obviously this is the Sahara Desert. We know we get a lot of meteorites out of there. We also will see meteorites from the Atacama Desert, I believe is like, one of the driest places on Earth. We will see meteorites from the Gobi Desert. And there are various deserts over the American Southwest, kind of spanning from California through Arizona and New Mexico. And those deserts are, vary quite a bit. But yes, desert is correct. You guys know what flag this is?
I don't.
Somewhere in the Middle East. Or
No.
Does it start with an M?
Morocco?
No, it starts with an A.
Algeria?
Oh, Algeria.
Antarctica.
Antarctica.
Oh, Antarctica, that's right.
Oh, wow.
I forget what it is. It's like true north or true south. Like you can see like the pointing up. Antarctica is actually, some people don't realize it, it's considered a desert. It's actually the world's largest desert. It's 13.8 million square miles. And 2/3 of the meteorites classified in the MetBull are actually found in Antarctica. Now, as we've discussed many times during our Hangouts, they do classify every single sample that they find. So the numbers are a little bit skewed, but they're doing that in the name of science. But there are a lot of different reasons why Antarctica is the best place to find meteorites. Now, not everybody can just go there, but one of the reasons is that the meteorites really stand out, like in the landscape. It's obviously very white there. It's a polar desert. A lot of the meteorites are dark, so they are easy to spot. And a desert isn't always hot. Like a lot of people think deserts are always hot, and they think of cactus and cacti and sand. But this is a polar desert. Deserts are more, it's more about the low levels of moisture. And that low levels of moisture are perfect environments for meteorites. So too bad we can't all go down there because I think that there are a lot of dense collection areas in Antarctica. I know that one of the things that they are working on is trying to locate more iron meteorites, but we'll discuss that a little bit more later. Okay, so for September of 2022, we had 220 meteorites approved and published in the MetBull. So of those 220, we had 219 finds and 1 find possible fall. And the reason I brought up Antarctica tonight was it's been a while since we've seen classifications coming out of Antarctica. It may be like the second time this year. They'll usually come in and big numbers. So yeah, 147 of those 220 were from Antarctica. So a lot of times I won't include the Antarctica in meteorites in my numbers. And I kind of cast that aside a lot. But this time I decided to pay a little bit more attention because it's a really cool place, and there are not a lot of stories you can pull up on the internet that you're going to get bored reading about Antarctica. It seems like a really cool place. I don't know that I'd be able to handle going there on an expedition, but I like hearing the adventures of people that do. So let's talk about the find possible fall. So that was Hassi El Biod 003, and that fell in Algeria, right there on the map. And no, as I put on the screen, I did not recycle that Sahara Desert picture. Those are different pictures, but they look very similar. But yes, that I believe that it was witnessed by maybe 3 people. So it hasn't been 100% confirmed. That may change in the future, but for now, it is technically going to be listed as a find with that side note of possible fall. Yes, so moving on. We had 27 different classification types. This is a little bit of a step down from the 2 previous months, but still some really good, awesome things happened in September. We had some meteorites that were approved by people on the crew. So that is exciting always. So here we are looking at some chondrites, carbonaceous, rumerudes, and enstatites. Now, again, the meteorites that you'll see are listed in 2 different columns. One's in September, and then the totals are literally the total number of meteorites, classifications under that type. So like the enstatites, they're 100, I think it's 140, and 60 of those are outside of Antarctica. All right, so we had, just a few of the carbonaceous, rumerudes, and enstatites. So moving on to some more chondrites. We had the L and the LLs, and very exciting. The most rare of the classifications on this entire page just happens to be our honorary Professor Pat's classification. Woo! And that is the LL4/5. And so I'm going to kick it over to Pat to tell us a little bit about that classification. Because there's something very unique about this one.
Yes, so say hello to NWA 15285. This is a meteorite that Topher bought for me during the days of COVID. This one he purchased in Quartzite, and he purchased it for me. And it has been in classification for a little more than a year. This one is, while it is a rare, a rare classification in count, it is not ultra special. It is an intermediate between type 4 and type 5. So it has some characteristics of type 4. Some of the phaolite numbers were more consistent with type 4, but some of the texture and the amount of recrystallization is more similar to 5. So it's an intermediate between LL4 and LL5. And this one I was honored with being co-classifier for. I did the chondral count numbers and the parent chondral size, and Daniel walked me through the microprobe work, and we arrived at the conclusion that it's partway between LL4 and LL5. That's the classification.
I was going to say that that's going to be a feather in your cap, Pat, because not many people can say that they are a co-classifier. That's congratulations. That's awesome.
It's amazing.
Thanks, Pat. Very exciting. All right, moving on to the H chondrites. All right, well, as you can see, most of these classifications have a lot of different meteorites under them, except for 2 of those. And that is the H3.5. There are only 21 of those, and the H4-AN, which is anomalous. So so on the last screen, we saw LL4/5. Now we're seeing a 3.5. Pat, can you kind of shed some light on what the difference is there?
Yes. So, 4/5 is an intermediate where it's, between 4 and 5 level of time under heat and pressure and metamorphism. It turns out that the amount of metamorphism that happens between 3.00 and 3.9 there's a significant difference there, and so we've added some new criteria. We as the community have added new criteria that break down the type 3s into finer gradation. And so H 3.0 through H 3.9, and it works for Ls and LLs as well, are just show relative amount of metamorphism. And so, we're looking at the chondrules slowly disintegrating and recrystallizing into stuff in the matrix, the area between the chondrules. And so this one at 3.5 is obviously halfway between 3 and 4, and breaks that down more finely. There's also some very, very low subtypes where it's 3.XX, and those are very valuable for science because they tell us they're unmetamorphosed since they were formed, and so they tell us more about the conditions under which they were formed. Thank you, Sue.
Thanks, Pat. Appreciate that. Yeah, that H3.5 is pretty rare. I did look that one up, and of the 21 listed there, 14 of those are from Antarctica, and one of them is literally listed the location as the Pacific Ocean. So, which we've discussed on past hangouts. So, yes, we have the Pacific Ocean as a location for some, and we even have the Moon and Mars on some others, but just a very few. I wanted to just take a minute to look at the H4 anomalous because as someone who is just kind of learning about the MetBull and understanding all the different features and things that you can learn, I started looking at that H4 a little bit. So there are 23 of those, and there are only 12 of those outside of Antarctica. And of those left, one of those is actually unknown. So of the 11 that were remaining, I thought it was kind of weird that 3 of them were found in Oman, because I don't really see Oman a lot, but Oman does have 19 dense collection areas, which 17 are actually in use. I didn't know there could be inactive ones. But yeah, and each of those H4 anomalies, I thought, well, did they find them all next to each other? And, they should have been paired instead of getting their own. So I looked them up to see if they were NWAs. Each one were named chondrites or named classifications. I thought, well, that's really strange, but they all come from different dense collection areas. And I still wasn't convinced. But I thought, well, it's the MetBull though. Like, this is, scientists have done a lot more deeper research into these than just me. So I'm sure there's got to be some explanation. As you can see on the map, like, they're really on the edge. Those the little yellow lines are the ones that I believe designate the dense collection areas. And as you can see, like, they're still really close in geography, but like not on top of each other. But here's the part where I realized, like, I was not onto anything at all, because in the MetBull, you can actually look up the O isotope testing if it's available. And as you can see, where they have the, all the little dots that are really close to each other, those are going to be where your main groups are. And the ones that kind of fall outside of those are going to be the anomalous. They don't have enough, features that are in common with the other ones. But as you can see, they may be both anomalous, but they're anomalous in different ways. So it was a coincidence. So I didn't find anything, really strange like I had thought. But like, that's how you can use the MetBull to, discover information like that. So it's a very powerful tool. Pat, I know that you probably know a lot more about this kind of testing than I do. So yeah, please give us some feedback.
Yeah, so the oxygen isotope testing is not done on every meteorite. It's only done on selected ones that are odd or unusual for some other reason. And very commonly, the oxygen isotope ratios on anomalous meteorites will be different. And see two great examples here. The oxygen isotope ratios speak to where the meteorite was formed, but the different areas in the protoplanetary disk and the solar nebula, and they have material from different places, whether they're closer to our sun or closer to other stars. And so anomalous usually means unusual oxygen isotope data. This testing costs roughly $450 per meteorite, And virtually all of it in the US is done by Dr. Karen Ziegler at University of New Mexico, Albuquerque. Thank you, Sue.
Thank you, Pat. Okay, moving on to the HED meteorites. As you can see, there are a lot of months that we won't see howardites, but there's usually an abundance of eucrite classifications and a little bit light on the diagonites in September. But yeah, anyways, nothing, too exciting there. So let's move on to the lunar, Martian, and just the other chondrites. And I will tell you that there's another exciting classification here, and that is the Martian knocklite. That is a classification. It was, I believe, the 29th at the time, but now there are 30. That was a Mark Lyon listed as the main mass holder, and Topher Spinnato, my husband, and Sean Mahoney listed as the other main specimen holders. And yeah, this knocklite is super cool, very unique. Like we've gotten so much positive feedback from everybody that's purchased it. They love looking at it under the microscope. They love the pieces that show the inside. They love the pieces that have the the fusion crust on them. They're all just really fantastic samples. So yeah, we'll talk about that a little bit more later.
And Sue, I just wanted to throw in there as well that we found out after the fact that they're magnetic, highly magnetic Mars.
Yes, who discovered that? Someone on the crew had mentioned that, I think it was Oz. But yeah, that was really unexpected. I have another question for Pat. Since we're here, I see it, that we had an ungrouped chondrite that was classified. So Pat, what's the difference between meteorites that are classified as ungrouped versus meteorites that are classified as anomalous?
Well, so this is kind of where the exciting science of meteoritics comes in. And the nomenclature is a little slippery, but in general, ungrouped meteorites show very different textural patterns when we're looking at the meteorite itself or at the thin section. And they temporarily get parked in ungrouped. And eventually, when we find enough meteorites that have similar characteristics to form a new group, so that's where things like CL and such come from, those new groupings. So anomalous, usually found by oxygen isotope ratios, ungrouped, generally found by looking at texture, but that's painting with a very broad brush.
I learned something new every time I hang out with you guys on Wednesday night. All right, so we reviewed the classifications. So let's look at the locations, and nothing too unusual here. As I always say, the usual suspects. Most of the classifications were found in either Antarctica, Africa, and Chile. Yes, so this is I usually like to make you guys guess the smallest total known weight, but for this month, I did include the numbers from Antarctica. And I really don't know if anybody would have guessed that there was a meteorite classified that was 0.95 grams. Yes. I went ahead and I looked up the smallest total known weight for September outside of Antarctica. So that one came out of the dense collection area in Chile. So just under 7 grams. Okay, so for the largest, as you see it there, it's 19.73 grams was the largest meteorite that was found in or approved in September. Yeah, so another eucrite, and I believe that the largest one last month was also a eucrite. I don't know if it was unbruciated, but it was the one that ended up totaling up to like 3 tons. So yeah, 2 months in a row, lots of eucrite out there. So I did promise earlier that we were going to discuss one of the classifications in a little bit more detail. Look at that beautiful, sexy, stunning meteorite. Mm-hmm. So that is the NWA 15200. And that is also known as the 200-gram knocklite. It total on weight is only 196 grams. So if you have some of this, consider yourself very lucky. This is the first meteorite that was actually ever classified as a Martian knocklite was called Nakhla. And it fell in Egypt in 1911. And as of today, November 2nd, 2022, of all the 30, it is the only one that was a witnessed fall. I'm as I said before on past Hangouts, if someone on our crew has already done a great job, discussing or teaching something, I'm not going to reinvent the wheel. And of course, who am I talking about? The awesome Mike Kelly, our on-staff geologist. He actually put together a Martian knocklite, a short 101 that we did on a Saturday night, and it was fantastic. We got a lot of positive feedback on that. We had people chomping at the bit to get a copy of it. He broke it down just in just the perfect way that the material was really easy to digest. So, like I said, I'm not going to reinvent the wheel. Go check it out, and you will be a Martian knocklite expert after Mike is done with you. Topher, tell me the one thing. Knocklite is something that is from the volcano, the magma.
Yeah. I'll
That's
be honest
really
with
cool.
you. It was something that I learned that knocklights form at the last reservoir of lava coming out of Mars. So it is down there deep and comes to the surface. And very volcanic, very highly magnetic, very cool stuff.
It doesn't look like it would be magnetic. I was surprised by that. I mean, I think everybody has their own opinion about it, but I thought it looked kind of diagonite, it's very green, it's really interesting
the
stuff.
actual interior is not magnetic. It is the fusion crust that is responds to a magnet, and that is what's really interesting about it.
Cool stuff.
Sorry, I'll jump in here. We have to remember too that all of the Martian meteorites and the lunar meteorites have been ejected from the surface of the planet or the moon by the impact of a regular meteorite. And so a lot of times the metal or the magnetic stuff in a Martian or a lunar is from the impactor that ejected it off the planet violently.
Wow. Yeah, I didn't even think about that. Thanks, Pat. Okay, you guys, when we first started this hangout, I mentioned in the beginning that we would talk about Antarctica a little bit later. So we're gonna do a deep dive. We're gonna spend a few extra minutes talking about this very unique place on our planet, the place that almost 70% of our meteorites come from, and every landscape is just stunning there. I'm sure that I would not enjoy the cold, as I love living in Arizona, but still really awesome to look at. So not anybody can just go down and look for meteorites in Antarctica. I'm sure that if you could, I know a few of the hunters that we personally know that would find a way to get down there. But you need to be part of, a funded and organized expedition group. A lot of these are, funded by governments, and a lot of them work in cooperation with each other. But the ones that there are a lot more than what I have featured during this hangout. But the ones that I featured during this hangout are the 4 that submitted meteorites in the last 12 months. But you can go to the MetBull and you can see that there are a lot there are a lot more countries that are down there, and as you can see, when I said they do work in cooperation with each other, like the NIPR Arbans, that is a joint venture with the country of Japan and Belgium. But yeah, so the last year we had Japan, Belgium, China, and the UK and the United States were all active down there. I'm going to turn it over to Pat. He's going to share a little bit with us about ANSMET and some of the other organizations.
Yeah, so ANSMET is run out of the principal investigator is in Case Western University in Akron, and we send a team. The U.S. sends a team down there every year. It's led by Harvey and Dr. Hardy, and they generally take researchers and graduate students, and they spend roughly 8 weeks on the continent and generally spend about 6 weeks in the field. And the other organization's CARE is from China. NIPR is Nippon Institute of Polar Research from Japan. And there's also have been Russians involved there as well. No classifications during the last year. But Antarctica is very unique in that it has a concentration mechanism that works really, really well. And so it concentrates the meteorites in very small areas. And at some point we can talk about how that mechanism works, but it's basically glaciers run downhill. At some point they just plop into the ocean with their meteorites. Other ones hit a little mountain range, turn upwards, and the snow and ice is ground away and the meteorites are just sitting there on the ground. But it's a brutal place to get to, and the time in the field, there's many days when you can't go out of your tent because the wind's blowing 50 miles an hour or 80 miles an hour, or occasionally 100 miles an hour, and that's in their summertime.
I actually read a story when I was researching Antarctica, and it was a gentleman talking about how hard it was to be sitting in the tent, and they had been stuck in it for 2 days because the wind was blowing so hard, and one of his partners had decided to cut bait and go home. I was like, wow. So it's not for everybody. As you can see, like some of the groups are a little bit more active than others, but I noticed the Lost Mets UK. I did read a little bit about what they're doing, and there is one particular type of meteorite that they don't find a lot of in Antarctica, and those are, iron meteorites. And there could be a number of reasons why, but one of the reasons that kept coming up is that when they're sitting on the surface and the sun is like beating down on them, they get heated up, and then they fall through the surface because they're melting, the snow underneath them, and they're going deep down in. And I think there are limits to how much you can be like drilling and digging into the ice sheets. So they are working on a metal detector that works a little bit differently, I guess, than a normal one. So they were putting a lot of time and testing into that based on what I was reading, I think. So I think that's why their numbers were a little bit lower this year. But I thought that was interesting. Hopefully they can find some really old iron meteorites once they get that process figured out. And another thing I thought was really interesting about Antarctica is these are the meteorites that were classified in the last, and I said 2022, but these are the meteorites classified in the last 12 months. And the dates there and the numbers, those are the meteorites of the years that they were found. So they literally put almost 200 meteorites through this year that were found back in 1974 through 1979. I thought that was really wild. So I don't know that much about it, but I am assuming that there are a lot more processes and red tape to get things classified if they're holding them onto them for decades, or maybe they're just knowing that they're not super significant, but they just need to get them recorded. Pat and I might be looking into that. We'll, get back to you in future, hangouts as we find out more. But yeah, there have not been in the last year, none of the meteorites that were submitted were found in the last 2 years. So just another little interesting fact that I noticed with my research. So there was one more thing that I did ask Pat, and he did have some feedback on, because as I was finishing up reading all this Antarctic stuff, I thought, hey, wait a minute. What about the other pole? Why are we not hearing about all the meteorites coming from, the North Pole? So, Pat, tell us a little bit about that before we say goodbye.
Yeah, so, we normally think about the Arctic and the Antarctic as being fairly similar, but in fact, they're really quite different. Antarctica is extremely mountainous. There are mountains well above 11,000 feet, and the concentration mechanism is about glaciers going downhill and hitting obstructions and turning up and forming these blue ice fields behind the obstruction. And that doesn't happen in the Arctic because the Arctic is flat. Also, if you drill a hole through the ice in the Arctic, you hit seawater every time. There's no land up there. It's ocean. It just has a bunch of ice floating on it. So it's the absence of that concentration mechanism that makes Antarctica so special, and the Arctic is not special for that reason.
Water is definitely not the ideal environment for meteorites. So thank you, Professor Pat. I like your jacket, very fashionable. All right, you guys. So that concludes part 3. Woo! I'm
Thank you,
caught
Sarah.
up.
Thank you so much.
Right.
I really enjoyed the teamwork between Pat and Sue. I think it's a good thing. So thanks, guys. Great job.
Yeah.
Thank you.
Well
Yeah.
done.
Thank you.
Thanks, guys. Excellent.